generalization. Thank you very much, Mark. Thanks for the invitation to speak here. This is joint work, as you can see. Let me see if I get this thing working. With Jan-Philipp Solovej. And
not working?
huh? It works. You see, but it's so tiny.
It's pretty tiny.
Yeah. But you have a bigger one? No.
I do have one.
Okay, well, let's go ahead. So now, one of the things I promised in the abstract is to outline the proof. And I do have the proof here, believe me. But maybe it will be better in the long run to spend some more time explaining the generalities behind this. And maybe I won't get to the proof. We'll see. Now, 35 years. Well, it starts with Wehrl. So let's do this. Yeah. So to quantify the inherent uncertainty of quantum states. So you don't have to know anything about quantum mechanics. Just Hilbert spaces. Alfred Wehrl, known to Friedel by his friends, in 1979, suggested a definition of the classical entropy of quantum states, and which was based on the Gaussian coherent state transform. Now I'll explain what that means. This has the advantage, one of the advantages is that the entropy that you get in this way for a quantum state is necessarily positive. Well, of course, the entropy of a quantum state always is positive. But if you make a classical approximation to a quantum state, which, for example, what Boltzmann did, you often end up with a negative entropy, which doesn't make a whole lot of sense. Whereas this definition always gives you a positive entropy. So it has some advantage. In addition to that, it has all kinds of nice properties about monotonicity and other things, which I will not go into. I will explain these things. Now, since it's positive, the question is, the question he asked is, which state, which quantum? Okay, we can try that. Then I'm going to have, where do we press? Yeah, that's better. So he conjectured that the classical entropy that he introduced, which is necessarily positive, well, of course, we'll have a minimum. That is, which quantum state will minimize this classical entropy. And he conjectured that it is minimized, this classical entropy of Wehrl is minimized by the same states that define the entropy, namely the Gaussian coherent states themselves will minimize the entropy of the Gaussian transform. Now, you might see an inconsistency in the dates here. I proved this in 1978. I proved this conjecture, which doesn't make sense since it was only published in 1979. But those days, sometimes papers took a long time to get published. And in fact, he sent it to me, and after a while, I proved it. So my paper came out before his paper. We didn't have the archive in those days, so things like this happen. And then I conjectured that the same result will hold when you replace these Glauber or Gaussian coherent states, the ones I've been talking about, by SU2 coherent states. I will explain what all that is. And by same thing, I mean that if you make the analogous definition of the entropy that Wehrl made, but you make it for SU2, then the entropy is positive, and there's a minimizer, and that minimizer is one of the coherent states itself. That was the conjecture. And that's what took 35 years to prove. Many people looked at that. Now, so I will present a short proof, which is joint work with Jan-Philipp Solovej. Well, you've heard that already. OK. Now, if I don't fall off this stage, we'll be OK. So first, I will describe coherent states in quantization, states of minimal classical entropy. Then that's for the usual, the old-fashioned Gaussian or Glauber coherent states. And then quantization of the sphere, which means introducing SU2. And a generalization of this conjecture. And it is through the generalization that one manages to prove the conjecture. That is, the generalization establishes intermediate steps such that the thing you want is the limit of all these intermediate steps. And each little intermediate step, it turns out, is provable. And formulation in terms of majorization of the main theorem, that is, an inductive argument, these are all parts of the proof, which I hope I will come to, but maybe I won't. We'll see. OK. Now, so this is a little tutorial on quantization. You can forget this. It doesn't really matter, except for this formula. So in general, to quantize something, you start with a classical phase space. We're going to go in the other direction. But for the usual historical context, you start with classical phase space. So what is a classical phase space? Well, it's a bunch of p's and q's. So it's a point, a state is a point in R2n. And then the p is position, momentum, and q is position. Don't ask me why. And let's think of n equals 1. That's perfectly enough. General case. Now, in quantum mechanics, instead of this R2n, we have a Hilbert space, which, for the beginning, at least for Wehrl, Alfred Wehrl, is just L2 of Rn. Again, think of n equals 1. That's the Hilbert space. That's where things take place. And what is quantization? Well, quantization is a function A which maps functions on this phase space into operators on H. That's what quantization is. It's this kind of map, and there are several maps you might consider. Now, among these quantum states, there are so-called pure states, which are simply projectors onto a single vector. A general state is an operator, or a density matrix to be more precise, but pure states are simply those which are projectors onto a single vector. And the rule is that the expected value of the, that the operator we're going to get, I haven't told you what it is yet, the operator we're going to get for a function on the phase space is given by, in a state psi, that is in a vector psi, is given by some map. Here's the map in which we are going to discuss right now. And one way to define this map is through the well-known Wehrl quantization, which is done by the Wigner distribution. But the trouble with that is it's not necessarily positive, although that's what's usually used. Another way is to use coherent states. Now, if all this is opaque, never mind. We'll get to some formulas pretty soon. OK. So, to be specific, let's consider this family of functions in L2 of R, or Rn, if x is a vector, a point in Rn. What is it? Well, this family of functions is parameterized by two numbers, or two vectors, if you like. These are the points in the phase space. But anyway, those are the parameters of this function. And what is it? It's a Gaussian centered at Q, so we know what that is, times e to the IPX. So it looks like it sort of combines Fourier transform, because when we integrate over P or integrate over X, we're taking Fourier transform. So it's something to do with Fourier transforms. You can sort of smell that. And it has something to do with Gaussian transforms. You can sort of smell it here. And we're doing the two simultaneously. So anyway, it satisfies this equation, but never mind. And the quantization map is the following. You take your classical function on phase space, here it is. You multiply it by the projector, that's this Dirac's notation for projector, onto this function in L2. And you integrate it over the classical phase space. That is to say, over R2n. N is take n equals 1. So that gives you the operator. And the expected value of this operator of the state psi, which I mentioned before, is simply obtained by putting psi on either side of this projector, which gives you that. So the map that we're talking about, that is the expectation value of the operator generated by the function, is this function of q and p, depending on psi, it's always less than or equal to 1. These guys are normalized in L2. That's what this guy is doing in front here. So it's therefore always less than or equal to 1 if psi is normalized, which you always think of it as being. And moreover, here's the interesting point. The integral of this with a 1 here, if you put a 1 there, you get this integral. That integral is 1. That is to say, the integral of this operator, dq dp, with a 1 here, is the identity operator. It's another way to say the same thing. All right, so if I give you a vector in L2, here's this psi, a function in L2. I compute this inner product, square it, and it gives me a function. And I can compute, and well, what do we know? The integral of this function is 1. It's a positive function, that's for sure. So it looks like a probability density in phase space. It's a function of Q and P. And we can compute its classical entropy. That is, what is the classical entropy? Well, everybody knows this formula. You take your function with a minus sign, multiply by the log of that thing, and integrate dp dq. That's the entropy of this classical entropy of this function, which is acting like a, which is, so to speak, a probability density. All right, so if I start with a general operator, which means I put a general function in here, I can also define this, but let's stay with this particular case. Now, it's easy to see, this is the important point. See, let me start that sentence again. What Boltzmann would say for the function on phase space that represents the state of a particle or whatever, the integral of that function is 1, but nobody tells you that the function has to be less than or equal to 1 in magnitude. It's just that its integral is 1 and it's positive. If it's bigger than 1, this expression is negative. If that happens, the integral can be negative. Not always, but it can be negative. And so Boltzmann's function plugged in here can often give you negative entropy. But since this guy is always less than or equal to 1, this quantity here is always positive, and so the entropy is guaranteed to be positive. Okay. Now, so since this is positive, we can ask which psi, this thing depends on psi this way, which psi in L2 will make this as small as possible. Okay? Now you can say, why did anybody ask this? Well, in 1979, people had time on their hands and they asked questions like this. It seemed like a sensible thing to do. Turns out to lead to a little bit of interesting mathematics.
What's the physics?
Sorry?
What's the physical meaning?
Well, an entropy, you know what an entropy is. So that's what you pay money to the electric power company for.
The inequality. You said
Huh? Sorry?
the extreme, you're asking an extreme of
Yeah, what's the physical meaning? Who knows? Nobody knows. It doesn't have any. The whole question has... But, you see, if we don't explore, we don't learn anything. And this no, I'm not just, I'm explaining. Coherent states, the use of these functions is used all over physics for lots of different reasons. It's a very good way to handle quantum mechanics. Not perfectly, but it's a very good way. And so when a natural, and this function, by the way, turns out was defined previously by Fushimi. When a natural question arises concerning these things, well, it's good to know what the answer is, even if you don't see yet what it's good for. It will come out eventually. Everything comes out eventually. All right, so here's the theorem, which Wehrl conjectured in '78, and which I proved, is that if you want to maximize this, minimize this thing, you take any of these f's itself. That is, you plug in an f. You take psi to be one of the f's. Any one, doesn't matter, by sort of a group invariance. And that will give you the minimum. So any other psi will do that. Now you can ask, for those who know about density matrices, I will not explain that, but for those who know about it, you can ask, what if I generalize this and have density matrices instead of a single pure state psi? Well, by concavity of entropy, which is a general fact, any density matrix can be decomposed into projectors. So if you're trying to minimize, the best thing is to take a single projector. That just comes out of concavity. So this is the minimum then over all possible density matrices. But if you don't know what those words mean, never mind, it's not important. Now the proof of this fact, back in 79, used two very deep facts in classical analysis, really deep, which had only been proved fairly recently, I mean in 78. One was the sharp constant in Young's inequality. You see, if you look at this thing, go back, what you want to do is you take this function of f, x, you integrate it against some psi, and you can see that this part of the integral, if you get the e to the ipx, is just this all ready-made for the sharp constant in Young's inequality. And this guy, if you forget the first factor, is ready-made for the sharp constant in the Hausdorff-Young inequality. And both of those inequalities have maximizers. And in both cases, the maximizers are Gaussians. So by pure luck, you can maximize both at the same time. And that's the proof of why this is the minimizer. Now, now, the new thing that comes out of our work here, which was not known before, is suppose instead of x log x, which defines the entropy, I take any function of this gadget. Not just x log x. Well, it was known that if the function is f of t is t to some power p bigger than 1, it was known that that would work, but or minus it. But that was all that was known. Now the new theorem is that any concave function will be minimized by the coherent state itself. So that's a new result about an old theorem. But that's not what we want to get into now. So let me write this down. So we have the integral of, let me write it this way, a projector in a Hilbert space. This thing is f, p, q. Can you see this board? Is that visible? Can you make it out? Yeah, back there? Okay. So this thing, you integrate this dp dq times 1. You get, of course, an operator on Hilbert space, and that operator is just the identity. That's one thing. And now if you put any function in here, p and q, well, you get another operator. And, and in particular, if you take, if you compute the expected value of that operator, you're computing psi p q psi psi, which is f p q psi squared. I'm just rehashing what I did. And that's going to be the classical function belonging to the vector psi. Okay. Now I want to migrate to SU2. Okay, so we look for at the representation spaces for SU2. So that's spin, as we call it. So the Hilbert space in that case is not L2 anymore, L2 of R anymore. It's L2 of little L2, 2j of dimension 2j plus 1, or C 2j plus 1, where j is 0 or a half or 1 or 3 halves, et cetera, et cetera. Those are the representation, irreducible representation spaces for SU2. Okay. Now, the Lie algebra, of course, everybody knows of these triplet of operators, Sx, Sy, and Z, which have representations on this space. And I want to try to repeat what I did before. So we take the classical phase space for is the sphere, S2. Now, SU2 has 4 dimensions, but One of them is just a phase, which goes out since I'm taking squares, so I don't have to worry about it. So there are only two left. And sorry, I said three. I have one left, two left. And that defines a point on the sphere. Now, take a highest weight vector in the representation. The highest weight vector is a vector, well, we can say it in the following way. If you take the spin, that is this triplet, dotted into a vector omega on the sphere, is a vector omega. You can look for a vector omega in the Hilbert space so that the eigenvalue of this operator on the Hilbert space is just j times the vector. That's the biggest you can get. And this whole thing is rotation invariant, obviously, so if I go through the group, if I replace omega by anything else of norm 1, I get another highest weight vector. So we're going to use all these highest weight vectors to define operators on Hj. So what do I do? Something very parallel to what I did before. I take a function on the sphere, here it is, times this projector onto one of these guys that satisfies that. And I integrated the omega. That gives me an operator belonging to a function on the sphere. Okay? Take an arbitrary function on the sphere, you get an operator. And what we can do is we can take a vector in the Hilbert space and do the analog of what we did before. That is, we take the inner product of the vector on the space. So think of this as L2, what I wrote down there, dotted into this highest weight vector. That's a function on the sphere now, which I denote by phi infinity. Y infinity you'll see in a minute. Y the infinity, V stands for the vector, and omega because it's a function on the sphere. That's the other thing. That's the analog of the function that I wrote down there. In any case, we can put an arbitrary function in here and get an operator. And it's a theorem that, in fact, given any operator on this Hilbert space, there is a function. So associated with this operator, there are two functions that on the sphere that I can find. One is the A that I have to stick in here to get the operator. And there is such. In the L2 case, there isn't. In the L2 case, you don't always get any operator. But in this case, you do. And moreover, this A is unique. I'll come back to that in a second. The other function on the sphere that I get for a given operator is simply its expectation value in the state omega, in the vector omega in this Hilbert space. So there are two functions that I get. The function that I need to generate the operator and the expectation value of the operator in a vector v, which I get by putting v omega in there, squared. OK. So what I conjectured way back was that if you take the entropy, namely this f is now x log x, take the integral of this function, this classical function, here it is. Forget this for the moment. If I take the integral of this classical function on the sphere, and with it times its logarithm with a minus sign, that's the entropy, the vector v that will minimize this entropy is itself one of these maximal weight vectors. Doesn't matter which one you take. That was the conjecture. That's like saying the vector that maximizes, or rather minimizes the entropy in the L2 case is itself one of these funny Gaussians with the e to the IPX. Well, the same thing is going to be true here. Okay, that's now. Okay. The new theorem is that, in fact, not only does that thing minimize, but it minimizes any concave function, not just minus x log x. But more is to come. Well, this was proved for j. For j equal a half, it's trivial. J equal 1 was not trivial. And that was proved by Schupp in 1999 and Scutaro in 2002, independently. But that's where the matter stood at the turn of the century. Now, so let me repeat. We take the representation of SU2. We look for highest weight vectors. We take the highest arbitrary highest weight vector, dot it into an arbitrary vector, square it, and try to make the integral of a concave function of that thing as small as we can. Okay? In particular for the entropy. Now the new feature that comes in here, which actually goes back to a paper that Solovej and I wrote, I don't know, around the turn of the century, which we called quantum coherent operators instead of quantum coherent vectors, is the following. You start with a Hilbert space C2j plus 1. The next thing you can do is for some fixed j. Instead of going from C2j plus 1, this vector space, into functions, you should think of the functions as a sort of an infinite limit of something in between, as I said before. And the in-between is the following. You go from j to j plus a half to j plus 1 to j plus, you keep going up by 1. And in the limit, when you go from j all the way as far as you can, in the limit, you'll get the classical function, if you're lucky. So the classical thing, which I'm interested in, this thing, is going to be the limit passing through a sequence of Hilbert spaces, a tower of Hilbert spaces, and taking a limit. And the same will be true going back for the coherent, the Glauber or Gaussian coherent states that I mentioned before. All right, and so here's how it works. So the phi that we defined is a map from a quantum state to a classical probability distribution. You take an operator A, you take its expectation value. That gives you a probability distribution. So we generalize this to completely positive trace-preserving maps, i.e. quantum channels, as it's called in the lingo of quantum information theory. They're called channels, because you imagine Alice and Bob at opposite ends of a telephone or something, and they're talking to each other. All right. So what are we going to do? We're going to go from J to something K, which is bigger. And I define little k as the difference of these two guys. Now, so I want to have a map from operators here to operators here to like that. And in the end, I'll end up with functions. All right. Now, you can also let k be negative, by the way, but I don't have it on this slide. But for the purposes at hand, little k is going to be positive. We're going to go up instead of down, but you can go in the other direction as well. So given an operator rho on j, on a C2j plus 1, let me tensor that with the identity on C2 k times. So that's an operator in here. But I have to symmetrize it because there are too many operators here. So what specifically speaking is how can I think of a vector in this in C2j plus 1? I can think of it as taking a vector in C1 half, or rather, yeah, C1. That is spin a half. Take a spin, which is either up or down. Take many of them and make them parallel. Or take any symmetric combination, symmetric vector in the tensor product j times of C1 half, or 2j times of C1 half. Well, I'm doing something very similar here, but in order to make sure that I end up in this space, I have to symmetrize it. That is, I have to look for the symmetric vectors. Otherwise, I'm somewhere else. Sorry?
In this case, your C2 has an SU2 action on it?
Yeah.
Yeah.
Right. Right. So this way I get anything I want. So C2j plus 1 is just 2j copies of C1 half, or whatever, you know what I mean. C, right, C2. Okay, but I have to make sure that I get the symmetric part. Otherwise, I'm in some other space. Now, all of this that I'm about to describe works very nicely for SU2. For SUN, or even SU3, it gets much more complicated. We don't know how to do the analogous thing. And we're hoping that some experts in the audience can figure out how to do this, what I'm about to say now, for SUN. All right, so, so this is what I do. Because of the symmetry, et cetera, there's a universal constant that I can put in front that preserves norms, that is, preserves traces. So this combination has the property that it's a completely positive trace-preserving map from C2j plus 1 to C2k plus 1. All right, so here's the theorem. For all j and all k, in this case k bigger than j, and all concave functions from 0, 1, and r, the trace over k of this function of the transformed vector v. So in this case, for rho, I put in the projector onto v. And what I'm about to say here would work for a general rho, except we know by concavity we may as well look at the particular projector case. Then this gadget is minimized when the vector that you take is itself one of these highest weight vectors. Doesn't matter which one, by group invariance. That's what was conjectured 35 years ago, but this is a more refined version of what was conjectured. So and the k equal infinity limit gives you the classical result that we wanted, namely if you just take functions, vectors times omegas, and which vector will maximize or minimize this f, the trace of f of integral over the sphere of this f, the trace becomes an integral. Well, you just get that by taking a limit, and this is the classical limit. So we get the thing we wanted in the first place by going from j to k, one step at a time. All right, so, but let me just pause for a moment with this formula. So we have this group SU2, and we have maximal weight vectors, and in a natural way they define coherent states. That is, any operator, turns out, at least in the finite dimensional case, any operator can be written, any operator in the representation space, or on the representation space, can be written as an integral over projectors onto the highest weight states, highest weight vectors. That's a theorem. And this is now true for this sort of Heisenberg group thing. It's true for SU2. We go so bold as to conjecture that it's going to be true for SUN. We don't know how to prove it, because there are complications that set in that don't apply to SU2. But the theorem is that if you take any concave function of a vector in the representation space dotted into the highest weight vector and integrate it, this is always minimized by a maximal weight vector itself. Now, I'm not a...
You need sort of some canonical quantization in order to get such sharp things. You wouldn't be able to go to an arbitrary quantum mechanical system.
No, sure. Arbitrary, no, but Lie, well,
what is the condition?
Lie groups. I don't know. I don't know enough about it. You're supposed to know. I'm relying on you. No, I mean it's a very important question. Yeah.
You are using the fact that there is a canonical quantization or some Wehrl quantization in the first.
No, we didn't use the Bargmann. Forget about the quant. I'm sorry I mentioned it.
You have up phi, up a phi in a product tree.
Yes, right.
The big one. Up a can't be defined in general. You can't quantize.
No, but what I can do, no, you're right. But what I can do and what I am doing, what I can do is I can take a highest weight vector.
I understand.
So forget about the quantization. That's just poetry that goes along with it. I'm sorry I put it. Maybe I should have put it at the end. Okay. And we're looking for a vector v in the representation space, taking this function now on the whatever, on the group, and integrating it, and trying to take a function of that which is concave, and trying to minimize this with respect to vector v with norm of v equals 1. This is what we're trying to do. Now, and the answer is that, yeah.
So for more general Lie groups, SUN or so, there is also the theory of coherent states.
Yeah, I'm sure.
You know, Barry had this paper on
Absolutely.
generalizing U's and so on.
Yes.
So is it still true that you can expand all the operators
Yes.
in irreducible?
I think so. I think so. This is, but forget about the operators. It's much simpler. Just ask this question. You have these guys, and you have choose a v to make this thing as small as possible. And the answer is, it turns out that v wants to be one of these guys for any concave function. Now, look, I'm not a group theorist, but it seems to me that something as general as that, if it generalizes to SUN and to other Lie groups, this must have some significance for representation theory. I don't know what, but I put it before you. I hope the experts will find it interesting and maybe do something with it. So let's see, how am I doing time-wise? Oh, I don't look too badly at all. Sorry. Yes, sir. Oh, I'm sorry.
So these maps by K, do they have some significance for quantum information people?
Well, I don't know about that, but I know that well, I know they have the following significance, not very significant, but they have it's a significance. Namely, if you take this, the original classical coherent state thing, so you go from operators to functions, and you want to compute traces of operators. For example, in statistical physics, you want to compute traces of E2, some Hamiltonian or whatever. You can use these coherent states to there's a theorem that goes along with it, that this trace of this e to this operator is bounded from one side and from the other side, either by the coherent, using the lower symbol of the operator or the upper symbol. That's a theorem that I proved, and also Berezin proved. Now, suppose you want to go, so here's the significance. Suppose you don't want to go to this classical trace, but you want to take, you don't want to go from operators on a Hilbert space to functions. You want to go from operators on a Hilbert space to operators on another Hilbert space. Now, one way you could do it is you can go up to the functions using the inequality in one direction, then come down to the operators in the other Hilbert space using the inequality in the other direction, which turns out to be lousy, but that's what you can do. This thing here tells you that you can go directly. So you can relate, you can systematically relate what happens to these traces, if you like, as you increase the dimension of the representation space without having to go up to infinity and coming down again. Okay, so for whatever it's worth, that's it. All right, and so, sorry. So this is, now, a theorem about general concave functions, integrals of concave functions of functions, makes you, or at least sums anyway. The fact that you have a general theorem of this kind makes you think of Karamata's theorem and makes you think of majorization. So what we're going to do is look at these maps. Sorry, getting confused now with the lasers. Okay, so we look at these maps, and these phi k maps, right, which that take you from one Hilbert space to another. Little k is the difference between big J and big K. So they're maps of, in this case, projectors onto vectors And there are two kinds of vectors I could stick in here. One is an arbitrary vector, and the other is one of these maximal weight vectors. So two things to consider. Well, so this map has eigenvalues. It's a map from vectors to vectors. So it has eigenvalues. And the claim is that not only is this thing bigger than that thing, but it's bigger in the following sense, that the eigenvalues of this guy are always bigger than the eigenvalues of that guy in the following sense of majorization. The biggest one is bigger than the biggest one over there. The sum of the top two is bigger than the sum of the top two over there, and so on. And that's a necessary and sufficient condition for saying that a function of these eigenvalues, a sum of functions of these eigenvalues, beats a sum of those for any concave function. That's Karamata's theorem. So, so I'm going to prove majorization. So I'm going to look at this map in detail and prove majorization. And that means that all these maps from J to K will have this concavity property. When I take the limit, I'll get the concavity property for the limit, which is for the simple functions. OK. So now it gets a little bit technical, I'm afraid. OK. All right. So the notation will be, I take a vector, I apply this channel, if you like, to it, this map. And these are the eigenvalues and eigenvectors of this map. And correspondingly, the same thing is true for an arbitrary one of these maximal weight vectors. I'll just put a C on there for coherent. Now, for these guys, you can actually work out what this map is explicitly, term by term. And you can compute the eigenvalues. You can write them down. It's not hard at all. So that's a sort of setup for an inductive proof. So for a given m, that is, m is the number of eigenvalues we're looking at. For a given m, the sum of the top eigenvalues of this guy over here is less than or equal, this is what we want to prove, is less than or equal to the sum of the eigenvalues for that special choice. And so we will use induction on m, but for each m, we'll use induction on k. Remember, little k is the difference between j and big K. So we're going to use induction on little k. Well, for little m equal 1, it's a triviality, so that's easy. You can write it down. So let's assume that this inequality that we want is true up to m minus 1. Use induction on k. It's an identity if k plus 1 is less than or equal to m, just because of preservation of traces, so that's easy. So it's OK for k equal 1. And let's assume it's OK for k minus 1. Sorry, I didn't say that correctly. That this thing, which is equal to this sum, where these are the eigenvectors, and that's the phi k. So we can write the sum of interest, that is this thing in this way, in terms of the eigenvectors. And now it gets a little messy. For this purpose, one has to explicitly write down the map, this phi k map. And the simplest way to do that, the most convenient way to handle symmetrization, remember there's this funny symmetrization that has to come in, is well, let me see how simply I can say this. You're going from a space of big dimension down to a space of small dimension. That is, you want this to be an operator on a space of big dimension, k, big K. So I have to know how to compute matrix elements of this map. And so I take a vector in the big K space. I annihilate little k of the spin-a-half particles that are sitting in a vector. Right? Remember, a vector in the big space, in any space, any of these representations, is a symmetric vector consisting of 2k plus 1 spin-a-half particles. Right? Or was it? Yeah, 2k plus 1. And so I have to eliminate little k of them. That will give me a vector, a symmetric vector in dimension j. Then I take the inner product with the given vector v, and then I go back again. So if you, with a little faith, and especially about this coefficient, with a little faith you can imagine that this funny thing, which systematically takes away vectors and preserves the symmetry, and then puts them back again, and takes the inner product with this projector onto v, that this ought to do the job, even if you don't know what bosons are. But it does. I mean, it's just, well, okay. So the sum of the eigenvectors of this gadget, this is the operator. Here it is. It's a funny kind of operator. And so the eigenvectors of this operator, we call them phi k. Those are the guys that you stick in for and after. The expectation value of those is the eigenvalue. So I'm summing them up. But now by induction, or just by looking, I can think of this as taking the product of k minus 1 factors on both sides, and then having done that, applied one more operation of one of these contractors. That'll get me up to little k. Okay? Now, so the sum of these eigenvalues is therefore can be thought of as taking the eigenvectors for the k and applying these a's and a stars on both sides, and that operation is called gamma. That's an operator. And so it's the trace of that operator against phi k minus 1. That is the thing we got by taking only k minus 1 of these symmetrizers, or annihilators. Now the operator gamma, this thing, you can easily check from the properties of these symmetrizers. It's just simple algebra, lies between 0 and 1 as an operator. And secondly, its trace works out to be this funny combination of k's and m's and things. Now, if you have an operator who is bounded by 1 and you know its trace, and you're trying to take the inner product of that operator against a bunch of vectors, then, sorry, this is the operator. The best thing, and you're trying to make this as big as possible, the best thing you can do is take 1, 1, 1, 1, 1, 1 as many times as you can. You're not allowed to go bigger than 1, but take 1, 1, 1, and what's left over goes at the end. That's a maximization problem. So we get an upper bound by just replacing all of this stuff by sticking. Sorry, by doing what I said, take 1, 1, 1, 1, that gives you this term, and what's left over gives you that term, and therefore the sum of these eigenvalues is bounded by the sum of the same eigenvalues with k minus 1, I mean for the operator with k minus 1, plus this thing left over. Now this recursion relation, it's a recursion inequality, whoops, I should have gone too far. Yeah, now, right, it's down here. So this recursion is an identity for when you take the maximal weight vectors for v. Turns out it's exact. So that tells you that simply by plugging in, you see that you do better. I mean, for the vector v, this is an upper bound, but for the coherent state vector, for the maximal weight vector, it's not only an upper bound, it's it. It's the correct answer. So the coherent state, the maximal weight vectors win. Now I realize all this is very obscure and it's not the usual mathematics, but it works. That's what counts, right? And and this proof does not seem to work, or at least not so far, for SU3. I mean, it's very specially cooked up for SU2. Okay, so that's the end of my song, really, except to talk about the classical limit. You just need a one-sided inequality to get it. It's written here. Let me not try to explain this. It's one side of the inequality I mentioned before by taking traces of functions of operators can be written as traces of functions of the expectation values of the operator as a bound, and that's what we're doing here. So, so that's enough. Furthermore, by taking the sphere and taking functions on the sphere that live very close to the North Pole, so functions peak near the North Pole, and taking a limit, you can get functions on L2 of the appropriate space. So you can therefore apply this maximization principle to the original Wehrl problem way back, which I announced way at the beginning, by taking a second limit. So where the heck was it? Somewhere. Yeah, here it is. And so that's the end of the story. And I just hope somebody will find this interesting enough to prove the conjecture that this should work, for, at least for SUN. And maybe it says something, I don't know what, about representation theory. But it's, I mean, something as general as that, you know, must have some meaning somehow, it seems to me. So thanks very much.
Thank you.